I've got an equation for another quadric surface on the board. Want to point out a couple of things that are different. First of all, this one's not centered at the origin. This one is going to have as its center 2, 0, 0. So when I'm looking at the planes that go through the center, I'm going to be concerned with the planes x equals 2, which is not the yz plane but parallel to it, y equals 0, which is the xz plane, z equals 0, which is the xy plane. Okay. Second, I want to point out that I've got all the variables on the left, and it's equal to 0. It is not equal to 1. And there's nothing I can do to make it equal to 1. If it was equal to 2, I could divide both sides by 2 and get a 1 here. Okay. But there's nothing I can multiply by to change that from a 0 to a 1. The only thing I could do would be to add 1 to both sides, but that's not particularly helpful because this is the part that involves my variables. Okay? So this is set equal to 0. Now, in the last video, we were talking about how you could count negative signs to see whether you had a hyperboloid in one sheet or two sheets. But I said make sure it's set equal to 1 before you start counting. Okay. That's because if it's set equal to 0, counting negative signs doesn't help. Let's take this equation and multiply both sides through by -1. Changes all the signs, but 0 is still 0. Here I had 1 negative sign, here I had 2. It's the same equation, it's going to have the same graph. Okay? So, counting negative signs isn't going to help. It's very different if this is equal to 0. And sometimes you'll see it with everything written positively, but one variable bumped over to the other side. So I've got one variable squared equaling a sum of the other two variables squared. So either of these would be a perfectly acceptable form for this equation. So this is going to be a little bit different. So let's go ahead and take a look and see what we get. So I'm going to start with the plane x equals 2. That's passing through the center, and that's going to be parallel to the yz plane. I want to make sure that I label this as parallel to the yz plane. I don't want to tell a lie and say that that is the yz plane. The examples we've done up until this point, I've kept things relatively simple, and since we were always centered at the origin, we were just always working with the coordinate planes. I don't want you developing the lazy habit that we always care about the coordinate planes. We don't. We care about the planes through the center. And that's really crucial in this case. Okay. Notice if I plug in x equals 2, that kills off this term, and I get y squared over 4 minus z squared over 9 equals 0. If I didn't plug in 2, if I actually looked in the coordinate plane, let's actually graph that as well, just so we can see what we get and talk a little bit about why it's not particularly useful. Okay. If I were to look at x equals 0, which would be the yz plane. Now I'm only doing this here to show you why it's not helpful. Okay, so this is not something you would actually do in graphing this. If I did that, if I plug in 0 for x, this becomes -2 squared, which is 4, plus y squared over 4, minus z squared over 9 equals 0. So I'm going to just move the variables over. That would be 4 equals z squared over 9 minus y squared over 4. That would be 1 equals z squared over 36 minus y squared over 16, because I divide both sides by 4. Now that gives me a lovely hyperbola. Okay, excellent. I could certainly take a look at that. That gives me a beautiful hyperbola. This does not, because that's not 1. Okay, so if I look at what I get here, this is something a little bit different. Now, I'm going to go ahead and just add over that z squared over 9. So I've got y squared over 4 equals z squared over 9. I'm going to take the square root of both sides. And I need to be very, very careful, because when I take the square root of a variable squared, I don't get that variable, I get the absolute value of that. So I'm getting the absolute value of y over 2, I can take the square root of 4, is equal to the absolute value of z over 9. And the way I can deal with that absolute value, or those absolute values, is by introducing a plus or minus. Okay. So I'm just going to say z over 9 is plus or minus, I'm sorry, z over 3, because I needed to take the square root of that 9. My bad there. Z over 3 is plus or minus y over 2. Now you might ask, why didn't I introduce a plus or minus in front of the z? Well, I could, but there are really only two possibilities. Either these guys have the same sign, which could be both positive or both negative, or these guys have opposite signs, which could be this one positive and this one negative, or this one negative and this one positive. So just introducing one plus or minus sign covers both possibilities. Okay. Now, if I take a look at this, that's not actually a hyperbola. I could solve for z and say z is plus or minus 3 over 2y. That's intersecting lines of slope plus and minus 3/2. So I'm getting intersecting lines. Now, intersecting lines happen to be a degenerate hyperbola. So if I get a degenerate hyperbola in this plane, I'm going to get a hyperbola. I'm going to get the same type of conic section in all other parallel planes. So when we did try plugging in x equals 0, which would give us a parallel plane that just didn't go through the center, we got a hyperbola, but it was not a degenerate hyperbola. It's going to be very crucial in sketching this that I see these intersecting lines as my cross section. We haven't seen any shapes so far that have had something like this. So if I were not to draw the plane through the center, but to just go blindly to the coordinate plane instead, I'd get the wrong trace, and I might very well draw the wrong conic section. Okay, excellent. Now, I've erased my equation. That was foolish. So let's see, it was x minus 2 squared plus y squared over 4 minus z squared over 9 equals 0. That was my equation. Okay, so this is the plane parallel to yz that passes through the center. So let's go ahead and take a look in the xy plane. Now that has as its equation z equals 0. And here I do want that coordinate plane because the z value at the center is 0 in this case. Now, if z is 0, that kills off this term. So I'm getting x minus 2 squared plus y squared over 4 equals 0. Now that does have a solution. 2, 0 is the only point that makes that true. Because this left-hand side is non-negative. It can be 0 or it can be positive, but the only thing that's going to make it 0 is if both of these terms simplify to 0. So we just get a single point. Now that's a degenerate ellipse, but when we get just a single point, that's our cue that it's time to move to a parallel plane. So I'm going to move to z equals plus or minus 3, which is parallel to the xy plane. And the reason I chose plus or minus 3 is because that makes z squared 9, so it makes this term 1, so that when I add it over, I'll have a 1. So that my equation becomes x minus 2 squared plus y squared over 4 equals 1. And with that 1 there, it's already in standard form. Again, if I made a different choice for z, I'd just get some number other than 1. I'd have to divide through by that number in order to get things in standard form. Okay, so now this is an ellipse. Now we're in a plane parallel to the xy plane. I can still label these as x and y. They're not actually the x and y axes in 3 space. These would be the lines parallel to the x-axis and the y-axis in this plane. In a similar way, for this trace here, even though we were in the plane x equals 2, I could have labeled my axes to say this one's parallel to the y-axis and this is parallel to the z-axis. All right, so this is centered now at 2, 0. And let's see, since I've got a 1 there, I'm going to come 1 over in the x direction. 4 is 2 squared, so I'm going to come 2 up and 2 down. And so this is the non-degenerate ellipse that I get in the planes z equals plus and minus 3. So in the xy plane, I'll have just a single point, but above and below it, I'll have a non-degenerate ellipse. All right, so let's take a look now at the, let's see, we've done yz, we've done xy, let's do xz. So if I look at the xz plane, where y equals 0, and again, here I do want the coordinate plane because the y value of the center is 0. So if y is 0, I'm getting x minus 2 squared minus z squared over 9 equals 0. Again, because that's a 0 and not a 1, this is going to give me a degenerate hyperbola. This is x minus 2 squared equals z squared over 9. I can take the square root of both sides, and I get the absolute value of x minus 2 is equal to the absolute value of z over 3. So z is going to be plus or minus 3 times the absolute value, times x minus 2. The plus or minus deals with both absolute values. All right, so if I draw that, that's again going to be intersecting lines. But instead of passing through the origin, they're going to pass through this point 2, 0. Okay, because that's where this is centered. And their slopes are plus and minus 3. So I'm getting something that looks like this. So 2 of my traces in the planes that pass through the center are going to be degenerate hyperbolas. If I move to parallel planes, I'll get non-degenerate hyperbolas, but those degenerate hyperbolas are going to be crucial in my sketching this shape in 3 space. Okay. So 2 sets of intersecting lines, 1 ellipse. This is the oddball. I'm going to draw that one in the middle. I like to, when I can, start in the YZ plane, or in this case, the plane that's parallel to it. Now, because we're not centered at the origin, this time I'm going to find it helpful to draw the axes first. The center was this point right here, 2, 0, 0. So in the plane that's parallel to YZ, which has just moved 2 forward from the YZ plane, I'm getting these intersecting lines. Something like so. Now, I can see right here in the XY plane, there's that single point that I got. But if I go above and below, I'm going to be getting ellipses that are not degenerate. So I'm getting something that looks like this. So we're getting this cone shape. If I didn't have those intersecting lines, if I had drawn non-degenerate hyperbolas, I'd think I had a hyperboloid. So it's very easy, if you don't work in the planes through the center, to get the wrong traces. Now, if I happen to come forward so that I'm in the plane, say, x equals 3, I will get a non-degenerate hyperbola as my trace there. If I go backwards to where x is equal to 0, we saw we were going to get a non-degenerate hyperbola, but it's the degenerate ones that are really giving us the shape that we get here. And then I can go ahead and draw in my third trace. Let's see, that would be the back. So in the xz plane, I'd have a line that goes from front to back, and back here I'd have one that goes from the back of that to the front of that. Okay. A shape like this is called an elliptic cone. If the ellipses happen to be circles, you could call it either an elliptic cone or a circular cone if you wanted to be more specific. In this case, I've got ellipses that are not circles, so I would have to say that this is an elliptic cone. And notice a cone is actually a double cone. It's got two halves to it, so make sure that we're drawing both of those halves.